Let's continue to talk about Taylor polynomials, see how we might use them, and learn Taylor's theorem and Taylor's inequality. So first of all, let's find a 7th degree Taylor polynomial to approximate f of x equals sine x near 0. So also, if we are approximating something near 0, so centered at 0, it's also called a Maclaurin polynomial. So a Maclaurin is just a special case of a Taylor polynomial when it is centered at 0. Now remember that to get our coefficients, we need the nth derivative. We would be evaluating that at 0 over, in this case then it will be n factorial, and then we've got x to the n. So this would give us the terms in our Taylor polynomial. We start with f of 0, but f of 0 equals 0, so our first term's actually 0. Then we're going to need some derivatives. So let's take the derivative of sine, which is cosine x, and evaluate that at 0, and we would get 1. If we did a second derivative, we would get negative sine x, and if we evaluate that at 0, we would get 0. Third derivative is going to be negative cosine x, and if we evaluate that at 0, we get negative 1. And fourth derivative is going to be sine x. Evaluating that at 0, we would get 0, and then we're going to cycle and continue as such. So let's go ahead and write down our Taylor polynomial of degree 7. Our first term was 0. Our next term would be 1 over 1 factorial times x to the 1, so that's just going to be x. Our next term is going to be 0. Our next term is going to be negative. We will have x to the third over 3 factorial. Then as we let n equal 4, we're going to have 0. If we let it equal 5, we're going to cycle back up here, so that's going to be plus x to the 5th over 5 factorial, and we can see the pattern developing here. 7 would be negative x to the 7 over 7 factorial. So here is a polynomial to approximate the sine function near 0. Let's look at a graph and see how it does. And that's actually pretty impressive. As we look at anything near 0, we have a pretty good approximation for our sine function. Now, as we did this, we initially started with, we had x, and x was not a very good approximation very far from 0, but it's very common in physics, particularly if we're looking at perhaps a pendulum with a small swing to it, to approximate sine theta with theta, because sine x does equal x if our theta or our x is very small, if we're near 0. Now, when we added on another term here, we've got this one that improved our approximation, and then when we got another term here, we improved it even more, and that's the idea with the Taylor polynomials. The more terms you add, the better you get for an approximation. So let's use this Taylor polynomial to approximate sine at 0.18. And the thing to note here then, if we did not have a calculator that did sine 0.18, we just got one of those really cheapy ones that can multiply, divide, add, and subtract, we could still find sine of 0.18 by using this polynomial. So we just need to put in 0.18 here, and then as we put it in the calculator, I get 0.179 and so forth. Now I also asked this calculator for the sine, and you can see to this many decimal places that I have accuracy. So that's pretty impressive for not very many terms to get that much accuracy. Now I was near 0, and so that improved the accuracy. If I wanted to find the sine and I started moving out here further, then I would not have that accuracy. So we want these near where this polynomial is centered, in this case 0. Well, how accurate are we? Well, let's look at the idea of the remainder. If we have a Taylor polynomial of degree n that's approximating a function, if we want to know how big the remainder is, we could just take the function minus the polynomial. Whatever's left is how far we missed by, so we call that the remainder. We're going to kind of look at that a little more so we can get an idea of how close we are. Here is a graph of e to the x, and then also some of the Taylor polynomials to approximate e to the x, and let's see their remainders. If we approximated this just by looking at its value at 0, which is 1, that's a pretty bad approximation. You can see our remainder is large, either positive or negatively. And as we start to get more terms in our polynomial, we can see that our remainder near 0 is getting very small. As we look at this green graph, we have a very, very small remainder until we get out here a ways. So let's look at Taylor's theorem. If a function has derivatives of all orders in an open interval containing a, then for each positive integer n and for each x in this interval, we have this is writing out our Taylor polynomial centered at a, and then we would have a remainder. And this says our remainder is this for some c between x and a. Now, if we wanted to continue on with our function and continue getting these, we wouldn't have just one term here, we would have several terms. So this is just telling us, though, our remainder is actually going to equal the nth plus 1 derivative evaluated at some c that's between a and x, and then having this same form. Well, that's quite interesting, and that might be reminiscent of the mean value theorem in some ways, because we're saying this is going to equal this for some c on this interval, looking at this derivative, and it is based on the mean value theorem. The proof of Taylor's theorem will follow this video. But from this, we can then get Taylor's inequality. And so if we look at this n plus 1 derivative at some x that's on some interval here, so our radius here of this interval is d. It could go plus or minus d on either side here. And if our x is on that interval and we have a bound for that, so if we can say the magnitude of that is less than or equal to some m, then the remainder will satisfy this inequality that the magnitude of the remainder is going to be less than or equal to this m, and then putting in the rest of this. And that is just simply because we could then have a bound for this piece, and that would be m, and we could replace that then with the m. So that's actually very useful because that will let us know how far we are off. We may not get an exact, but we can at least get a bound, and we could say, I know I am at least within this much of the function when I use this Taylor polynomial for an approximation. Let's actually see the proof of Taylor's inequality for n equal 1, and then it will be true for n plus 1, and we could continue with that, which is we do following this video, but let's see it now for n equaling 1. So let's go ahead and look at the proof of this for n equal 1. So if n equal 1, we want the magnitude of the f of the n plus 1 derivative, so that would be the second derivative, bound by something less than or equal to m. And we're going to just look at the positive case here, and so we're looking at this on the upper half of this interval. And we could go ahead and integrate both sides. We could replace this with the t, so we could integrate from a to x. So we have this interval where this would be true up to our x. So let's go ahead and do that. By the fundamental theorem of calculus, if we integrate this derivative, we would get f prime of t evaluated from a to x, and that would be less than or equal to mt evaluated from a to x. So that would be f prime of x minus f prime of a less than or equal to m times, and this would just be x minus a. Now we can move this over. We're going to replace these variables with t again, so we can integrate from a to x then, and so we'll use t for our variable. We're going to basically just do this one more time then. So we're going to have integral a to x of f prime of t dt, and that's going to be less than or equal to integral a to x, we move this over, f prime of a plus m t minus a dt. So as we do this integration, this is going to leave us f of t evaluated from a to x, so that's going to be f of x minus f of a, and that will be less than or equal to, this would be f prime of a t, so that's going to be f prime of a x minus a when we do the upper and lower limits there, plus, now looking at this piece, this is going to be 1/2 m t minus a squared, and that would need to be evaluated between a and x. So that's going to give us 1/2 m x minus a squared, and you can see when we do the lower limit that that's just going to give us 0. So now that we have that, let's look at the remainder. We know that the remainder, if we're looking at n equal 1, is going to be the function minus the Taylor polynomial at 1. Well, let's go ahead and write out what that is. The Taylor polynomial at 1 would be f of a, and then we would have plus the derivative at a times x minus a. And I do need to subtract that because this negative would distribute to both. So it would be the derivative a times x minus a. But whoa, let's look at this for just a minute. This remainder is actually exactly what we have here if we move this term over. So this, with this moved over here, is the remainder. So let's go ahead and write that down. So all of this piece is the remainder when n equal 1, and that's going to be less than or equal to 1/2 m times x minus a squared. Now we could do a similar argument and take this and look at the other piece with this absolute value. So we could look at where we had f double prime of x was greater than or equal to negative m, and we would get a similar thing. So we can make the statement then, if we looked at absolute value, that the absolute value of this remainder is going to be less than or equal to 1/2 m and then absolute value of x minus a squared. Now we didn't need the absolute values on this piece, but we're going to put them on there because now as we go to show that this is true, we showed it was true for 1, and we'll want to show that it's true for n plus 1. So we want the form that works whether this is going to be positive or negative. And the complete proof of this will be following this video.